How do we know that our type systems are right? The way you make sure is called a type soundness theorem. And a type soundness theorem says if you've got an expression that is your whole program, so you start out in an empty context, and there is a type for it, that is type check returns a type, then interp of E will never produce an error. That is, you'll never get an attempt to add a number to a function, because if you tried to do that in your program, the type checker would have rejected it. Sometimes this statement, never produces an error, is a little too strong. For example, if you have division in your language, then the type checker probably cannot rule out divide by 0. And so sometimes the soundness theorem says if an expression has a type, then running E doesn't produce an error except the following potential errors, like divide by 0. Right? So again, soundness is making sure that your type system is right, making sure it does what it's supposed to do, which is to ensure that certain kinds of errors never happen. If soundness fails, if you can't prove this theorem, or if you find an example where an expression T has a type and E does produce an error, that means your type system is broken. And in fact, both of our types extensions for today are slightly broken. The letrec checking that we've done has a bug because if I say f has type num arrow num, then when I type check f, it'll have num arrow num. But the way our interpreter works is we temporarily set f to 42, and we'll look up the 42, reinstall that as f, and now we'll end up trying to apply 42 as a function, which is exactly the sort of thing that our type system was meant to rule out. You should never get a can't apply a number as a function error. There's a couple of ways to fix this. One is to change letrec, change the grammar of letrec so that you can only write functions on the right-hand side. And that way you will never refer to the name that you're defining too early because lambda always just returns an immediate closure. So if you do that, that will fix the problem. You won't be able to have a letrec form that exploits the intermediate 42. Another possibility is just to say that, well, one of the things the type system doesn't rule out is trying to use 42 as a function. Or maybe it's a little better to introduce an undefined value instead of 42 and say that the type system rules out exceptions except that you might get an attempt to use undefined when you expected a number or a function or some other thing. Right? And that's in fact what I've implemented in the interpreter. And type checker that you can download on the web page. The type checker does not constrain the right-hand side to functions, and so there is a possibility of getting an undefined value used where you expected some other type at runtime. Our type checking for let type also has a bug in it, and this one is more subtle. Here I have an application, this curly brace is an application, of the result of this type to the result of this let type. This let type defines foo locally, and it returns a function that wants a foo as an argument, where foo has variance a and b. This expression defines type foo, and it returns a foo, foo constructed of type, constructed with a. And so this expression has type foo. This is a function that wants type foo as an argument. According to the type system, everything is fine. We're passing a foo into a function that wants a foo. But of course what was wrong here is that the notion of foo here says that a has a number inside, while the a that we constructed has a function numbers to numbers. And so we're going to end up with an error where we try to add 1 to a function. Again, adding 1 to the function is the kind of error that was not supposed to happen. And the problem here is that we've allowed foo to be locally defined, but twice in 2 different locations, and those different locations can flow together. Possible solutions are don't have local definitions. All type definitions have to be at the top, at the outside of the program. And so if you have the same definition twice, you can just flag that as an error. Another possibility, and the one that's implemented in PLA typed and ML and similar languages, is that you can't return a type out of let type that mentions D. So the idea here is that outside of this let type form, foo is not useful. There's nothing you can do with it, because you've already escaped outside of the area where foo is available. And so the adjustment to the type rule is to say that tau0, the result of let type here, doesn't have D anywhere inside of it. D immediately, or a function that wants a D, or anything like that. And with that refinement to the type rule, as implemented in the code that you can check on the web page, then this program is rejected as not having a type because foo shows up. It tries to escape right there.